The proton-proton chain reaction is one of two nuclear fusion reactions, along with the CNO cycle, by which stars convert hydrogen to helium and which dominates in stars the size of the Sun or smaller. In general, proton-proton fusion can occur only if the temperature of the protons is high enough to overcome their mutual electrostatic or Coulomb repulsion. In the Sun, deuterium-producing events are rare as diprotons. The much more common result of nuclear reactions within the star immediately decay back into two protons. A complete conversion of the hydrogen in the solar core is calculated to take more than 10 years. History of the theory. The theory that proton-proton reactions are the basic principle by which the Sun and other stars burn was advocated by Arthur Stanley Eddington in the 1920s. At the time, the temperature of the Sun was considered too low to overcome the Coulomb barrier. After the development of quantum mechanics, it was discovered that tunneling of the wave functions of the protons through the repulsive barrier allows for fusion at a lower temperature than the classical prediction. Even so, it was unclear how proton-proton fusion might proceed, because the most obvious product, helium-2, is unstable and immediately dissociates back into a pair of protons. In 1939, Hans Bethe proposed that one of the protons could beta decay into a neutron via the weak interaction during the brief moment of fusion, making deuterium the initial product in the chain. The idea was part of the body of work in stellar nucleosynthesis for which Bethe won the 1967 Nobel Prize in Physics. The pp chain reaction. The first step involves the fusion of two 1H nuclei into deuterium, releasing a positron and a neutrino as one proton changes into a neutron. It is a two-stage process. First, two protons fuse to form a diproton, followed by the beta plus decay of the diproton to deuterium. With the overall formula, this first step is extremely slow because the beta plus decay of the diproton to deuterium is extremely rare. The half-life of a proton in the core of the Sun before it is involved in a successful pp fusion is estimated to be 1 billion years. Even at the extreme density and temperatures found there, the positron emitted by the beta decay is almost immediately annihilated with an electron, and the mass energy, as well as their kinetic energy, is carried off by two gamma-ray photons. After it is formed, the deuterium produced in the first stage can fuse with another proton to produce a light isotope of helium-3 He. This process, mediated by the strong nuclear force rather than the weak force, is extremely fast by comparison to the first step. It is estimated that, under the conditions in the Sun's core, a newly created deuterium nucleus exists for only about 4 seconds before it is converted to He3. From here there are 4 possible paths to generate 4 He. In PPI, helium-4 is produced by fusing two helium-3 nuclei. The pp2 and pp3 branches fuse 3 He with pre-existing 4 He to form beryllium-7, which undergoes further reactions to produce 2 helium-4 nuclei. In the Sun, the helium-3 produced in these reactions exists for only about 400 years before it is converted into helium-4. In the Sun, 4He synthesis via branch PPI occurs with a frequency of 86%, pp2 with 14% and pp3 with 0.11%. There is also an extremely rare PPIV branch. Additionally, other even less frequent reactions may occur. However, the rate of these reactions is very low due to very small cross-sections, or because the number of reacting particles is so low that any reactions that might happen is statistically insignificant. This is partly why no mass 5 or mass 8 elements are seen, while the reactions that would produce them, such as a proton plus helium-4 producing lithium-5, or 2 helium-4 nuclei coming together to form beryllium-8, may actually happen. These elements are not detected because there are no stable isotopes of mass 5 or 8. The resulting products immediately decay into their initial reactants. The PPI branch, the complete PPI chain reaction, releases a net energy of 698842829381850484026.732 MeV. 2% of this energy is lost to the neutrinos that are produced. The PPI branch is dominant at temperatures of 10 to 700714000000000000000000000000000000000000000000000000000000000000000000000000000 14 mK. Below 7007100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The PP2 branch. The PP2 branch is dominant at temperatures of 14 to 7007230000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000by the reaction. Rather, they are the energies of the neutrinos that are produced by the reaction. 90% of the neutrinos produced in the reaction of 7b to 7 Li carry an energy of 69871373953070000.861 MeV, while the remaining 10% carry 6986613359452099990.383 MeV. The difference is whether the lithium-7 produced is in the ground state or an excited state, respectively. The PP3 branch. The PP3 chain is dominant if the temperature exceeds 70072300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 but was very important in the solar neutrino problem because it generates very high-energy neutrinos. The PPIV branch. This reaction is predicted but has never been observed due to its rarity. In this reaction, helium-3 reacts directly with a proton to give helium-4, with an even higher possible neutrino energy. Energy release. Comparing the mass of the final helium-4 atom with the masses of the 4 protons reveals that 0.007 or 0.7% of the mass of the original protons has been lost. This mass has been converted into energy, in the form of gamma rays and neutrinos released during each of the individual reactions. The total energy yield of one whole chain is 698842826177497510026.73 MeV. Energy released. His gamma rays will interact with electrons and protons and heat the interior of the Sun. Also, kinetic energy of fusion products increases the temperature of plasma in the Sun. This heating supports the Sun and prevents it from collapsing under its own weight. Neutrinos do not interact significantly with matter and therefore do not help support the Sun against gravitational collapse. Their energy is lost. The neutrinos in the PPI, PPII and PPIII chains carry away 2.0%, 4.0%, and 28.3% of the energy in those reactions, respectively. The PEP reaction. Deuterium can also be produced by the rare PEP reaction. In the Sun, the frequency ratio of the PEP reaction versus the PP reaction is 1 to 400. However, the neutrinos released by the PEP reaction are far more energetic, while neutrinos produced in the first step of the PP reaction range in energy up to 69866729141245400000000.42 MeV. The PEP reaction produces sharp energy line neutrinos of 698723071341412799991.44 MeV. Detection of solar neutrinos from this reaction were reported by the Borb collaboration in 2012. Both the PEP and PP reactions can be seen as two different Feynman representations of the same basic interaction, where the electron passes to the right side of the reaction as an anti-electron. This is represented in the figure of proton-proton and electron capture chain reactions in S*, available at the NDM-06 website.